In today's data-driven world, innovation and data integrity are the drivers of success. At Infineon, we believe this is only possible when high-performance components are delivering the highest levels of reliability. At almost every step in the digital and the analog world, we generate data that our devices collect and analyze. With a growing global population, faster digitalization, higher connectivity requirements, and huge amounts of collected data, the demand for reliable and sustainable data centers is greater than ever. Improving their overall energy efficiency not only reduces cost, but also has a positive impact on the environment. The role of data centers in our lives is evolving. Because of digitalization and the ongoing push for artificial intelligence, they will need to provide more services to more people. This will require a vast amount of information transfer, driven through both regional data centers and edge computing. To meet these demands, Infineon offers market-leading DC-DC converter solutions that support quick design-in options while providing superior efficiency, power density, and robustness. We offer flexible digital controllers with a superior transient response. Over 1 billion of our best-in-class power stages were sold into high-reliability, high-efficiency systems. They integrate Infineon's MOSFETs and can optimize total system solutions from DC to V-Core. Our smart and high-efficiency POL converters are designed for smart enterprise systems. We provide you innovation for best-in-class efficiency, telemetry, transients, design flexibility, and robustness. With our semiconductor solutions for data centers, we're also contributing to a greener and better planet. Part of your life, part of tomorrow. Infineon.
And good morning, everyone. My name is Yuchen Su, and I'm very glad to be here today. And thank you very much for giving me this opportunity. And today, I would like to talk about the topic, my research topic. The research on the modular multi-level converter-based solid-state transformer. Okay, and firstly, I would like to briefly introduce myself. I received a bachelor degree from National Tsinghua University Department of Electrical Engineering in 2015, Taiwan, and then I received a PhD degree in 2021. And so in total, I studied National Tsinghua University Department of Electrical Engineering for about 10 years. And I was mainly directed by Professor Paul Tai Chen, but unfortunately, he encountered some health problem which make it difficult to continue advising me. So finally, I was transferred to Professor Chong Min Liao, and he helped me finish the oral defense and my graduation. Okay, actually last month, I just come back to Taiwan, and I also visit my previous university. And here shows the, sorry, maybe I forgot to say, this topic is the work I did when I was a PhD student. So it's a little different from the work now. So I present my PhD students' work. Sorry, I forgot to say. Okay, and so here shows the entrance of my previous university, and this here shows the photo taken on this date. Okay, and here shows the main research when I was a PhD student, the Modular Multilevel Cascading Converter, MMCC. Okay, and among them, the single stop bridge cell SSBC is the most famous because it has several advantages. For example, it requires no high voltage devices, and it requires no state-out transformer. And also, it can achieve the good output performance because of its multi-level output. But obviously, the main drawback of this converter is the requirement of a large number of power devices and the capacitors. So in order to further improve these drawbacks, we then try to integrate several edge bridge cells into one 3-phase 2-level cell to further reduce both the component count and the capacitance demand. So therefore, accordingly, the hybrid cascading converter was then developed and be regarded as a promising topology for utility interface, which is the reason why I would like to do this research. And okay, here shows some of my publication about this topic, like a journal paper and several international conference papers. And here also shows the test bed established for my main research. And as can be seen, the voltage and the current are all well performed as what we want, like a multi-level output and the current with low THD. Okay, and actually last year I was a visiting scholar in Tokyo Tech with Professor Makoto Hakiwara as my advisor. Okay, and actually in addition, last year I also tried my best to network with other scholars from both academia and the industry in Japan, like Professor Wada from Tokyo Metropolitan University, and I also met several engineers from the Fuji Electric company. Okay, and so this is the reason why I can now have a chance to continue my postdoc research in Japan in Tokyo Metropolitan University, and with Professor Keiji Wada as my advisor. And here shows a photo coming from my professor's Twitter. Okay, so after the self-introduction, let me start my presentation today. Okay, and here shows the outline of my presentation. And firstly, I would like to introduce the research background of my presentation. Okay, and here shows the schematic diagram of the microgrid. Okay, and what is microgrid? Maybe in short, it can mean that maybe in an area, the power maybe can be generated by itself, and the generated power can also be used by itself. So the power loss from the long distance transmission can be greatly reduced. For example, like this figure, the power required by the building maybe in commercial or residential area can be directly generated from the nearby renewable energy, like wind power or solar power. But however, in such a microgrid, as can be imagined, the surplus and the shortage of energy are both probable in this area. Okay, yes, as can be imagined. So in this situation, the utility interface also plays an important role in energy exchange with the utility grid. It's just a little similar to the concept of maybe we can buy some electricity from the grid, or we can also sell the electricity to the grid. Okay, so here shows the construction of the utility interface. And traditionally, for example, the PV panel will be connected with the power converter, and then the power converters are then all connected in parallel to collect the generated power. But however, even after the parallel connection, the voltage here still belongs to low voltage. So an additional step-down transformer is also required for the connection with a high AC voltage grid. But as can be imagined, the step-down transformer is usually bulky and costly. So in order to remove the bulky step-down transformer, the new utility interface has been developed recently by connecting all the converter in series rather than in parallel. So then now the low voltage here can be directly added together and directly connected to the high AC voltage grid. By doing so, we can find that the bulky step-down transformer is not required anymore. Okay, so following this concept, the so-called solid-state transformer (SST) has then been developed and widely discussed in the field of power electronics. Okay, and the SST basically consists of several AC to DC converters connected in series. Okay, and also include several isolated DC-DC converter for the purpose of course, isolation. So this is also the reason why this converter can be essentially regarded as the transformer, because it has an isolation. Okay, and so the SST basically can be applied for power generation, and it can also be for power generation like a PV panel. It can also be used for like a power consumption, like EV chargers. Okay, but it's a little unfortunate that basically they are independently operated. So there seems also to be a possibility to further combine them together. For example, like this figure, like this picture, the possibility of SST for further integrating both PV panel and the EV charger together seems to be feasible and worth discussing, because by doing so, the overall footprint may be further reduced. So accordingly, here shows the proposed SST for integrating PV panel and the EV chargers together, which looks a little like the two parallel connected cascading converters. Okay, and in the proposed SST, the proposed SST is characterized by the integration of upside power flows from both PV panel and the EV charger. In other words, maybe for example, the PV power generation, the power flow direction is this direction, but EV charger consumption is this power flow direction. So namely, the proposed SST features the flexibility in addressing upside power flow directions. Okay, so now I would like to talk about briefly talk about the system configuration. And here shows the system configuration, which is called the Modular Multilevel Converter (MMC). Okay, and now firstly, you should be known that the MMC is composed of multiple chopper cells instead of H-bridge cells. Okay, and slightly different from the general MMC, the discussed MMC has no DC source requirement and a DC link. So that the overall system now should be investigated from the three-phase point of view, because it's an open DC operation. Okay, and besides, each phase of the MMC can be defined as a leg, and half of the leg can be defined as an arm. And the leg power regulation should be investigated from the horizontal viewpoint, and while the arm power regulation should be investigated from the vertical viewpoint. Okay, so in this way, the power flow relationship of the MMC can be comprehensively understood. And here also shows some related papers. Okay, so in order to proceed with the power flow analysis, the circuit should be firstly simplified. Firstly, each arm can be simplified as a voltage source with the corresponding current. Then, following the KCL and the KVL rules, the voltage and the current equations can be expressed, and they are the basic of the power flow analysis. And it is also important to know that now, because as what I just previously said, the DC bus here is in fact virtual. So the circulating current among three phases, the circulating current should satisfy the KCL equation. This KCL equation, namely the three-phase circulating current summation should be 0. Okay, so with the voltage and current information, the power flow analysis can be done. Okay, and here, firstly, for convenience, the discussed MMC is simply called the open DC MMC. Okay, and in the open DC MMC, the grid voltage, the grid current, the circulating current, and the zero sequence voltage can be listed here with the corresponding components. Okay, and the grid voltage and the grid currents may contain positive and the negative sequence component. But the circulating current may contain not only a positive sequence and negative sequence component, but also the DC circulating current components. And meanwhile, the zero sequence voltage is also may also be included. So then, with this information, the relative power can be derived by multiplying the voltage and the current together. Okay, and so first, here directly shows the result after the calculation, and here shows the average power. First, it shows the average powers of upper arm and lower arms, and we can here is upper arm, it has lower arm, and interesting, we found that they can be separated into three power parts: the DC side power, the AC side power, and the arm power. Okay, and then we then the average power of phase leg can be derived by adding together the upper arm and lower arm powers. And we can find that in this way, the arm powers cancel out. So now only the DC side power and the AC side power are included in the phase leg. Okay, and furthermore, the average power of the overall system can be derived by adding together the 3 phase leg powers. So in this way, we can find now only the AC side power exists and DC side power disappear. Okay, and in addition, the difference between the phase power and the average overall power can also be derived like this. We call it phase clusters. So we can find in this way the power difference, including of course the DC side power, but in addition to the DC side power, some AC side power are also included, and I define it as the cluster power. Okay, so until now, firstly, I can summarize the above mentioned result as this schematic diagram. Okay, and we can find that in short, the AC side power. Firstly, the overall power comes from the AC side and then evenly shared to each arm. And besides, if the leg power regulation is required, maybe the DC side power and the cluster power can both be used for the regulation. But however, we can find that the arm power, we can find from the calculation, the arm power is cancelled out. But namely the arm powers haven't been carefully investigated at this moment. So especially we can find each arm power seems to be independently operated. So then the next issue is how to ensure the arm power, regulation with the summation of the circulating currents to be 0. How to achieve this requirement? So about this problem. So firstly, we do some literature review and found there seems to be 2 possible methods. And the first method is to combine fundamental and the third order circulating current together. But the premise is we need to inject additional third order zero sequence voltage, which is a little complicated. So in my research, this is not taken into consideration. So on the other hand, I found second method is to combine positive sequence and negative sequence fundamental circulating currents. Okay, and about this, here I use an example to explain how it works. Okay, assuming the power regulation is required only by A phase. The voltage and the current will now be in phase for A phase, as shown in this phasor diagram. But however, in order not only to cancel out the A phase current, but also to make sure no power is generated at B phase and C phase, the only way is to make the voltage and the current in quadrature, namely in 90 degrees. So now like a B phase and C phase, a B phase voltage current in 90 degrees and C phase voltage and current in 90 degrees. So by doing so, we can find that the 2 requirements can both be satisfied, but the operating current now may contain both the positive sequence and negative sequence components. Okay, and so we focus on this method first. Okay, so following this concept, the next step is to find out the general solution for the arm powers. Okay, and first of all, the power difference between arms can be derived as these 3 power equations for A phase, B phase, and C phase. But however, we can find that with here totally 4, 1, 2, 1, 2, 3, 4, with totally 4 current variables, the unique solution cannot be obtained with only 3 power equations. So therefore, we can additionally add another reactive power equation, which means the total reactive power difference. With this additional equation, the relationship between the powers and the currents can be represented in a 4x4 matrix. And basically, the 4x4 matrix is constructed from the voltage component listed here. Okay, and then the four current component can be easily solved out using the well-known Cramer's rule. And they are respectively the positive sequence and negative sequence circulating current components. Okay, and finally, after finishing the power flow analysis, we can summarize the final power flow relationship as this table and also this figure for more straightforward understanding. Okay, and besides, the component we can use for the controller design are also listed here. The overall voltage control can be achieved by the positive sequence grid current, and the unbalancing control can be achieved by the positive and negative sequence circulating current component. And moreover, the lag balancing control can be performed by 3 components. They are respectively the negative sequence grid currents, zero sequence voltage, and the DC circulating current. Okay, and in addition, it should also be known that the remaining components like VP, VN, and E are also necessary for the feed-forward design. Okay, so now next let me talk about the presentation. Sorry. Let me talk about the proposed SST, the operation. Okay, sorry. And okay, with the information derived from the power flow analysis, the proposed control scheme can then be designed based on the well-known hierarchical control structure. Okay, including the overall, lag, and arm, and the individual control. And here shows the block diagram of the hierarchical control scheme. So from which the final voltage reference can be obtained. Okay, but it should be known that now the lag control only the DC circulating current will be regulated for lag balancing control. The reason is that because the zero sequence voltage and the negative sequence current are both not the best choice from the practical point of view. So here only the DC circulating current is taken into consideration. Okay, and here for better understanding of the basic operation, the single phase representation can be used to graphically illustrate the power flow relationship among PVs, EV, and the grid. Okay, and here I try to use some example to illustrate several possible operating points. For example, like this case, when the power generation from PV is equal to the power consumption of the EV, the power can be directly transferred from PV to EV without passing through the utility grid. Okay, and of course, in this case, if there are no power generation and no power consumption, basically no power flow among them. And in this case, when the power is generated from the PV panel but not required by the EV chargers, the generated power can be sent to the utility grid. And similarly, when the power is required by an EV charger, but no power is generated in the PV, the required power can be supported from the grid side. Okay, so in the same way as can be imagined, in this case, maybe half of the extra PV power generation will be sent back to the utility grid, and in this case, half of the extra EV power consumption will be supported from the utility grid. So as can be seen, the power flow relationship are very easy to understand. Okay, and here I use the simulation to check the performance. Here shows the simulation platform, the parameters, and similarly upper arm represent the power generation, and the lower arm represent the power consumption. And now the DAB here is used to is used to show one type of the isolated DC-DC converters. Okay, so firstly, very similar. We can find in this case the PV, the power generated from PV is directly sent back to EV. So the current only flowing between upper arms and lower arm, and no current flow to the grid side. Okay, and of course in this case no current flow. Okay, and in this case we can find PV power generation can be sent back to the grid side, so no current in the lower arm. Okay, so and similarly in this case the grid current supported the EV charger and no current flowing in the upper arm. Okay, so and in this case, can find PV can set the power to EV and the grid. So the upper arm's current magnitude is maybe twice the magnitude of grid side and the lower arms. Okay, and this is also similar. The EV chargers current is maybe twice of the magnitude is twice the magnitude of grid side and the upper arms. Okay, so obviously the simulation result perform well in agreement with what we want. Okay, so until now, all of the discussion is basically based on the normal operation, normal condition. So what will happen when the grid fault condition occurs? So is there any challenge for it? So is this also to be an important issue, because the grid fault is impossible to be fully excluded. So firstly, in a simulation platform, I quickly test the system with the single phase 100% voltage set and check the performance. And we can find that now, although the grid current is still balanced, but the upper arm and the lower arm currents become severely unbalanced, which will make the system easily trigger the overall current protection. So obviously, this is not a good phenomenon. Therefore, the grid fault challenge of the proposed SST should be carefully discussed. So firstly, for better understanding of the reason, we firstly use one case study example to explain where it comes from. Okay, and the left side is the 2,700 watt normal operation. Okay, and we can find now the power is basically evenly shared among three phases, and as can be imagined. Okay, but however, when in the right side, when the system encounters a single phase 100% voltage set, the grid side powers become unbalanced. So the power flow management is now required. Okay, so firstly, we check from the horizontal point of view, and we can find now the lag power regulation should have been done. And from the simulation result, we can find that the 3 DC circulating current perform exactly as what we want. And if we more detailedly check the right power here, okay, it can be observed that the power compensation for the three phases make the grid side power become balanced again. Yeah, now we can find now the power become balanced again. So if so, the next question maybe why there still exist unbalanced components in the upper arm and the lower arm, because now already become balanced, why there still has the unbalanced component. So now in order to find out the reason, we then try to check the power flow from the vertical point of view. Okay, and sorry, let me check. Okay, so as previously described, the fourth AC circulating current component can be obtained from the 4x4 matrix. So, and because we can find now the power among three phases is balanced. Now the power is balanced among three phases. Yes, we can then put this value into the matrix and calculate the four components. Okay, after the calculation, we can find the result is like this. And now we can find not only the positive sequence component, but also the negative sequence component appear. So from which the reason is clarified why there is also included unbalanced components. So on the other hand, how can we do to avoid the unbalanced circulating currents? Of course, it means that maybe the negative sequence AC circulating current component should be set 0 like this. Yeah. So now, for example, if we set the negative sequence component to 0 and only the positive sequence component, and let us check what will happen if we put these values into a matrix. So similarly, we put this value into a matrix and calculate the power, and we can find interesting. Now the newly derived power is like this, and okay, and if we put this result to the figure, we can find that something interesting is that now the grid size power is exactly the same as the newly derived power. Okay, that is to say, if the DC side power can be accordingly regulated following the grid conditions, the fundamental circulating current will be kept balanced regardless of the grid fault conditions. Okay, so here shows the comparison before and after revision. So sorry. Here shows the comparison in normal operation and in grid fault condition. So with the so first here I quickly use the simulation result to check the performance. So before the revision, we can find that even though the grid current still be unbalanced, but the upper arm and lower arm is severely unbalanced. But after revision, we can find the upper arm and lower arm current become balanced again. Okay, so for sure, the case study example is exactly not enough and must be extended to any possible conditions. Therefore, the quantitative discussion should also be carried out. So unfortunately, it is found that the power ratio among the arms can be determined based on the grid voltage information coming from the first column of the 4x4 matrix. Okay, so the result is like during the balance operation, the power can be equally shared among three arms, but during the unbalanced operation, the power may be unevenly shared among three arms because we need to regulate the DC size power. Okay, and finally here shows the tabular comparison in mathematical way to highlight the difference. Okay, and firstly, when a system is a three-phase balance voltage, of course, in both the grid current and the circulating current, there are no negative sequence component included. But however, when the system suffer from single phase 100% voltage set and without DC side regulation, we can find the grid current, of course, is still no problem, but the circulating currents now including negative sequence circulating current component, and even it may include some DC circulating current component. Okay, and this undesired component can be fully eliminated if the DC side regulation is included, namely if the DC side power are properly regulated. And we can find now only the positive sequence component and no other undesired component. And furthermore, we can also find that this the value here is exactly the same as here. It means that maybe even with the DC side regulation, the unbalanced power with the DC side regulation, the unbalanced operation can perform exactly as the same as the balanced operation. Like this, the unbalanced operation is capable of performing like a balanced operation. This is also another another advantage we found from the analysis results. Okay, so finally, we once again use a simulation result to confirm the performance under unbalanced grid condition. And firstly, in this case, we can find in single phase voltage state, the current becomes severely unbalanced, but with the DC side regulation, it can become balanced again. And we can check the component details, and we found that in left side, there are negative sequence component, but now become zero with the DC side regulation. Okay, and similarly, in this case, we can find that the unbalanced, the upper arm and the lower arms current become very severely unbalanced, but with the DC side regulation, it can become balanced again. And now originally you may include the negative sequence component and also the DC circulating current component, but now the negative sequence component becomes zero, and the DC circulating current component also becomes zero. Okay, and similarly in this case, the current also very critically unbalanced, but now become balanced again, and negative sequence component and DC circulating component can both become zero with the DC side regulation. So obviously, the simulation result also perform in well agreement with what we want. Okay, and finally, I will also like to experimentally verify the feasibility of the proposed SST. Okay, and following the system parameters of the simulation platform, the test bench has also been established in the lab, like this photograph. And here shows the parameters, and similarly, the upper arm represent the power generation, and the lower arm represent the power consumption. And also, I use the DAB converter to simulate the isolated DC-DC converters. Okay, so firstly, under balanced operation, we check the three possible operating point, and this point, this point, and this point, and we can find it can perform exactly as what we want. Okay, and even during the unbalanced operation, like a single phase grid fault, a single phase 100% voltage set, we can find without the DC side regulation is become severely unbalanced, but now become balanced again with the DC side regulation. Okay, and similarly in this case, without and with DC side regulation, it can make the system become balanced again. And similarly here, also make the system become balanced again. Okay, so the experimental result also perform in agreement with the simulation result. Okay, and maybe only okay. And finally, this part I quickly run through, and here just shows some maybe the research work maybe further extended in the future. So here shows some potential research topic and the topic I would like to do in the future. Okay, and here just shows the figure. This figure just shows the system configuration of the microgrid interconnection. We can find that basically because the microgrid, basically the microgrid has different voltage magnitude and the frequency. So if for the connection of two different microgrid, maybe we should use the interlinking converter as a buffer, and here use the HVDC transmission to help the connection of two different microgrid. And similarly, the SST we discussed may also be connected to respective microgrid. So the final target is I would like to do in the future is to explore the possibility of further integrating the interlinking converter and the SST like this galvanic diagram. And maybe some of the advantages can be summarized here. Especially, the main feature is that maybe it has a possibility to integrating different kinds of applications like HVDC, AC microgrid, and also renewable and battery use. Okay, I think this is my presentation today. So thanks for your listening. maybe we can move to the Q&A time. Okay.
Yeah,
Thank
thank
you,
you very
Dr.
much for very nice presentation. Yeah.
Okay, thank you.
Is there any questions from the audience, please?
Or maybe we share the
Probably you keep the slide screen
Yeah.
on with the
Yes, sir.
probably the summary or the layout.
Okay, so maybe here.
Thank you. Okay, I'll begin with the questions. In the talk, this was quite interesting. We talk about the control of the components of the power in the system. It was interesting that you did most of the talk about how to do the balancing control and how to control the circulating current, arm currents, etc., without the DAB.
Yeah.
And then suddenly you added the DAB structure. So just a curiosity from my point of view. When you don't add the DAB, it was possible to control on the balancing. That's all right. But why do you need the balancing control when you have that kind of DAB structure? Because normally with the structure, the DAB will naturally balance the output because you have the input in parallel.
Okay, so I think maybe the first question is maybe about without the DAB, maybe the system can still achieve this kind of performance. I think the answer is maybe no, because this research is very interesting. Is that because without the sorry for a minute. Okay, for the originally for the maybe previous, basically for the original MNC like this without any DAB converter, the only way to balance in the system is to use like the circulating current or the like a grid current components. So without the DAB, maybe we should use the circulating component to help balance the system. So it will make the system like maybe encounter like this kind of very unbalanced conditions. Namely, the system is from the grid side, the system is balanced, but in the up run and low run, it becomes a little severely unbalanced. But there's no way to do it because this is required for the system balancing. But with the DC, with the DAB converter, namely we can get additional control freedom from the DAB. So if the DAB can also be used to regulate the power, now the system can make this kind of unbalanced component for balancing reduce, and also only use the DAB converter to help the system become balanced. So with the DAB converter, the system can, it means that maybe the system's burden can be greatly reduced because the device or the system protection may be not so easy trigger. So without DAB converter, maybe this kind of performance cannot be achieved. But with DAB converter, it means we can get additional control freedom to help the system. Yes, this is my answer about the first part. And the second question, I a little forgot. Can you say again?
The second question is about the balancing of the capacitor with the DAB. Usually it's naturally balanced because you have all the input in parallel and the output in series like that. Not normally it's natural balance.
Yeah. So basically DAB part, for example, because now you can find that now the DAB part is basically parallel connection. So it means that maybe, for example, here is the 900 watts. We can equally share the each phase DAB to be 300 watt, but we can also change the operating power among the three phase DAB, like maybe 100 here and here 500 and here 400 like this. So I use this kind of control freedom to help the system's AC side unbalanced to become balancing again. So basically, maybe similar, just as what the chair say. Basically, normally, naturally, when the system becomes naturally balanced, maybe DAB, it should be equally share the power. But we can also intentionally change the possible power sharing among the three phase DAB. So we use this kind of control freedom to help the system. So this is my answer, because now it's parallel connection, so it can achieve this kind of regulation.
Okay, thank you. Is there any other questions? Okay.
Yeah.
I'll
Actually,
continue. Yes.
during waiting other people, so I have a question. Yes, so thank you very much for very nice presentation. I think that you do very good job during the PhD. Yeah, many work and many publication. And my question is about the frequency, switching frequency. So now in the system, you work with the 2 kilohertz and maybe 12 kilohertz. So
Sharper cell.
yeah, so how to say, like, why you select this frequency, and should we work with higher frequency? For example, we use the SIC, so yeah, possibly we can work with higher.
Yes. Because this is the characteristic of the MNC, because in my system I use the phase shift PWM. Phase shift PWM means maybe the carrier frequency, or the carrier among the different cells. Maybe the carrier have a certain phase shift angle. So by doing so, the carrier frequency of each cell can be set very low frequency, like here I only set 2 kilohertz, but with the help of the phase shift PWM, the equivalent switching frequency can be very high. So it means that maybe we can use very low frequency operation in each cell, but achieve the relatively high switching frequency. So in my opinion, if I use the SIC or some new technology device, we can make the cell to operate in maybe higher frequency, and in this way, the equivalent switching frequency can be further higher. So if the equivalent switching frequency become further higher, maybe the volume of inductor can be reduced. Can be further reduced because the equivalent frequency become higher. So it's also a possible way to make the system to the overall system volume to be greatly reduced. So this is my opinion. So if you use a SIC, maybe you will make the system better. So but I choose the low frequency is because previously in my previous laboratory we only use like IGBT. So basically the frequency cannot be set too high. So but with the help of the phase shift PWM, even though the low frequency operation of IGBT, but the equivalent switching frequency can still become very high. So the inductor we selected here is also not to use, or it's also no need to use the so big volumes inductor.
yeah, thank you very much for your sharing and comment.
Okay, thanks.
So, yeah, does anyone have a question?
Jushan, so sorry, I was want to ask a follow-up question with Dr. Van Lang Phạm questions. So
Okay.
with higher switching frequency, would it allow for the cell capacitor to reduce? You can see now you use like millifarad capacitance, so it's like hundreds of megahertz, hundreds of kilohertz like switching frequency. Does that drop the cell capacitance?
For in my about the capacitor is a little different from the carrier frequency part here, because the capacitance volume here is related to the for example if the power, because here maybe the capacitance will include the power component, like a fundamental frequency power component or double frequency power component, because this reason. Wait a minute. Sorry, maybe this part I don't carefully shows in this slide, but yes, because we can find that the maybe like this. Yeah, because we can find that the voltage here and the current here, basically including the AC component and also DC component. So if for the power calculation, maybe we can, for example, the AC multiply AC will including the DC component and also double frequency component. But if the DC circulating current, DC component multiplied by the AC component, it will including the fundamental frequency component. Namely, the capacitance should handle maybe very low frequency component in the capacitor. So the capacitor is very difficult to be set very low value, because it should handle the very low frequency component, low frequency power component in each bridge cells. So this is the reason maybe capacitor cannot be reduced too much, because it should handle the power, the maybe some low frequency power components.
Oh, I see. So like the cell capacitance still need to sustaining the grid frequency. That's what you're saying, right?
Yeah.
Change the AC.
Yeah, because we hope the capacitance module to be DC, and if we hope the capacitor to be DC and not to change too much, so we should set the capacitance to be a certain value to make sure maybe only the voltage variation only within maybe 5% to make the system easily operating.
I see.
Yes.
Yeah, thank you.
Thank you.
I see Kang has a questions. Kang, please unmute yourself and ask your questions.
Hello.
Hello.
Yes, thank you, Mr. Su, because of the really interesting presentation. I have two questions. So I see the DC link voltage is just 450 volt. So with this voltage, so you select 15 microfarad capacitance. Is it quite high? And my second question is the MMC is for grid voltage application. So have you consider about the grid frequency variation? Because as far as I know, with the MMC topology, so the frequency change is really sensitive problems. Is it right?
Yes. Okay. So first, so thank you for your question. And first question is about, yes, maybe as you say, the cell capacitance seems to be a little over designed, because we can find that basically we make the capacitance variation very maybe too low. Basically, maybe no voltage variation, because we select the too big, too large capacitor, but it's a little over design actually, as what you say. But the reason is that at that moment, because originally we want to operate the system maybe to be higher, to be like a 5 kilowatt or maybe higher, but maybe due to some limitation of the campus, maybe the voltage cannot be used so high. So we after buying the capacitor, but we found we can operate to too high power rating. So we have nothing to do but to decrease the power rating. So it make the capacitor to be maybe a little over designed. So can found basically the capacitor with no variation and very good performance. But in fact it's a little over designed. Yes. And the second question is about the grid frequency variation. But this part I haven't carefully considered, because in my controller we use the phase lock loop to tracking the actual grid frequency. So it means that maybe even though the grid frequency has a slightly variation, the phase lock loop can still well tracking the grid frequency variation. So basically, maybe not so much influence on my controller. Basically, it's not so much influence on my controller. But in fact, if the grid frequency variation to be too big, and maybe if the phase lock loop is not well designed, maybe the tracking will still have some problem. In fact, so this part maybe is also worth discussing, and maybe in the future this part maybe also be taken into consideration. Now I only consider the voltage, the grid voltage magnitude maybe has some grid fault, but the grid frequency fault I still not so consider so much actually.
I got it.
Thank you.
Thank you for your answer.
Yeah, thank you.
Is there any other questions? Time? Yeah, it's about time. Probably we can ask one more questions. Okay. I'll just continue with the discussions. It is very interesting now because you show the capacitor voltages already, which is nice with the oversizing capacitance. But I wonder if you actually operate at the rated power, then you see the fluctuation at 120 Hz. Yeah, and it will be phase shift between each phase leg, right?
Yes.
So let's bring me to a bit concerned about the DAB operation, because the DAB usually have the highest efficiency when the input voltage and the output voltage have the same ratio. But now at the output, you have a lot of voltages with a slight difference in voltages, which is all right. But when you reduce the capacitance or the ripple becomes significant, for example, 20%, then I suspect that you will have to face some difficulties in your control or efficiency of the DAB design or something like that.
Yes. Yes. Just as you mentioned, maybe when the capacitor, maybe I choose maybe the correct value capacitor to, maybe it means the system voltage maybe included some voltage fluctuation, like so it will also maybe affect the DAB part. Yes. So in my opinion, maybe yes. So in this way, if I want to keep the voltage here to be the same, the efficiency certainly has some influence, because maybe we cannot make sure the DAB can always operate in the like a soft switching range. Yeah, so maybe this is also a good question. Maybe
Probably for your next research, probably you have a problem in controlling the DB as well, because the dynamic of the DB is quite slow. I'm not sure if you can follow the 120 Hz ripple, but probably you can consider that during your postdoc period with Professor Wada.
okay, thank you. Yeah, actually now in my postdoc, I also do, I just focus on DAB part, so maybe the topic is a little changed. But now I can also focus on the DAB part.
Okay, yeah. Best of luck. Okay, thank you. I think it's time. We can switch to the second speaker.
Yeah, thank you very much for first presenter, and thank you very much for chairman. So yeah.